All right, this is our last new lesson of the unit. This is Unit 2, Day 4. Our topic today is called Average Rate of Change. Suppose you take a car trip from St. George to Salt Lake City and you record the distance that you travel every few minutes. The distance that you travel in that case is a function of the time or how long you have been traveling. If you graphed your position versus your time, the graph might end up looking something like this. So on the x-axis, we have, it's kind of hidden down there, we have the time in hours, and on the y-axis, we have the distance that you've traveled in miles. So at time 0, we've traveled 0 miles. So this sort of represents starting out in St. George, down in that at the origin. And up on the other end, up here, after traveling for 5 hours, we have traveled a total of 300 miles. This would represent when we arrive in Salt Lake. Now, it's not just a straight line, you might have noticed. And hopefully you've been maybe thinking about why the graph might have this shape, which is a little bit different than you might have thought it would look like. First of all, I'd like to think about maybe what our average speed was for the trip. How fast were we traveling? How many miles per hour on average? Well, we traveled a total of 300 miles. And normally when we're thinking about speed as we're driving, we would think about that in terms of miles per hour. Well, per in math usually tells us that we're dividing. Miles per hour means essentially to take the miles and divide it by the hours. So we traveled a total of 300 miles, and we did that over a time of 5 hours. So for our trip, on average, 300 divided by 5 is 60 miles per hour. Now maybe that's a little bit slower than you thought it would be, or maybe you're thinking to yourself, I hope people aren't driving 60 miles per hour on the freeway. But that 60 miles per hour is just the average speed. So we have these periods where you might have noticed you are not traveling any farther between, I don't know, like almost time 1.5 and pretty close to 2 hours. For that time period, you traveled 0. So maybe that represents when you take a pit stop in Beaver. So you stayed there for a little while. And again, you have this time right here that you spent not moving forward, and that is sort of when you stopped in Spanish Fork for another pit stop, either to fill up on gas or get a snack or something. So because you have these periods of time where your speed is essentially 0, you're not traveling, that brings your average down a little bit to 60. So let's look at the average speed between Beaver and Spanish Fork. Well, right here represents when we leave Beaver, and here represents when we arrive in Spanish Fork. And I have these 2 points listed down here. You can use the points to help you if you want. And if we think, again, we're thinking about speed, so I want to know how many miles over how many hours. Well, in this case, between Beaver and Spanish Fork, it's about 150 miles, and you could either sort of eyeball that from the graph. The distance here is 150 miles, or you could look at those points down there between 100 and 250 miles. And the time that it took, if we eyeball it, it's about 2 hours. And again, the point down here sort of confirms that it's a 2-hour difference. So we're going to divide that by 2 hours. And that means between Beaver and Spanish Fork, our average speed was 75 miles per hour, which is at least what the speed limit used to be. I should update the problem to reflect the 80 mile per hour speed limit. But it's 75. We averaged 75 miles per hour between Beaver and Spanish Fork. Now, there weren't any stops during that time, so that's probably more representative of the speed that you were traveling on the freeway. And this idea of finding an average, this is what we're talking about today when we talk about average rate of change. This first average speed we found, 60 miles per hour, that's essentially what our graph would look like if we averaged out those hills and valleys, if we sort of made it a straight line instead of this curvy line. And again, this 75 miles per hour is what it would look like if we looked at this straight line instead of the curved line. So average rate of change, when we talk about average rate of change, we always talk about it for a specific interval between two x values. And what we're interested in knowing is what the slope is between those 2 points on the graph. And the equation looks like this: f of b minus f of a over b minus a. Now that equation probably doesn't look very familiar to you. It's written in function notation, so it's saying the value of the function at the x value b, subtract the value of the function at x value a, and divide that by b minus a. But you actually have seen this formula before. You just saw it written a little bit differently. And this is how you may have seen it in the past. And you might recognize that as the slope formula, because really average rate of change is all about finding the slope of what's called a secant line between those 2 points. If you averaged that curve out and made it just into a straight line, it's the slope of that line. So let's look at how we can find the average rate of change for a function. We're going to start by looking at functions that are represented as graphs. So here is function f of x. It's a parabola. And we want to know the average rate of change over a couple of different intervals. And again, the interval is sort of important. This first interval is from x equals 1. So on our graph, that's right here, the point 1, 4. And we want to find the average rate of change from 1 to 3. Well, here is the point 30 on our graph. And again, these are x values. So you can see maybe that the function is decreasing. Well, it's decreasing, in fact, by a value of 4, and it's going over by a value of 2. So if we're finding the slope of that line, if we average out that curve as a line, it would be that it's going down 4 over 2. And if we simplify that, negative 4 divided by 2 is negative 2. So the average rate of change of this function over the interval from 1 to 3 is negative 2. The negative part of that means that the function is decreasing over that interval on average. And the number, the 2, sort of tells you about the magnitude of the decrease. It's, a bigger number there means it's decreasing faster, and a smaller number or fraction there maybe means that it's not decreasing very quickly. So let's look at another interval, the interval from x equals 4 to x equals 7. Well, here is where x equals 4 on our function, and way up here is where x equals 7. So if we're finding the average rate of change between those 2 points, I can't draw a very straight line. We're essentially finding the slope of that sort of line that I drew. And if you think about that slope, this thing is going up 15, and it's going over 3 units. And 15 divided by 3 reduces to 5. So the average rate of change for the interval from 4 to 7 is 5. So you can see the interval makes a big difference. On our second interval, this function is not decreasing at all. It's increasing, and it's increasing pretty rapidly. The last one, from -1 to 5. I'm going to erase a little bit here. So for x equals -1, we have a value of 4 on the function, and for x equals 5, we have a value of 4 on the function. So if we think about the line that would connect those 2 points, if we average it out, the slope of this line is it's going up 0 and it's going over 4. And that simplifies to 0. So maybe you're thinking to yourself, that's kind of weird. It goes down and then up, but the average rate of change is 0. Well, it sort of ended up at the same height that it started. So even though it went down a little, it went up an equal amount. So it averages out to be an average rate of change of 0. Okay, here is one more practice with looking at average rate of change on a graph. So we have, let me make that bigger. We have a graph showing the number of campers that are camping at a 3-day music festival. And this graph happens to show 20 years worth of data. So right here is 1 in the x direction. That represents the first year. And it looks like they had maybe 12 or 1,300 campers. All the way to the 20th year, where they had something like just under 4,000, maybe 3,800 or so. So our question is, we would like to calculate and interpret the average rate of change over the interval from 3 to 9. So between year 3 and year 9. So the 2 points on the graph that we're thinking about are this one right here, and for year 9, right up here. And since it's a graph and it's not a particularly, there's quite a big interval here between our y values, so we're going to have to eyeball it a little bit. So if we think about the slope of this line, if we approximate it with a line, it looks to me like it's going up a little over 500. Maybe we could call that 600. So this is the interval from 3 to 9. It's going up around 600. And it's going over 6. So we get an average rate of change of approximately 100. So in terms of this music festival, what that means is that between the 3rd and the 9th year, on average, about 100 more people attended each year, or that the attendance increased by an average of 100 per year. I can't fit that word here. Increased, sorry. Okay, so we have one other interval that I want to think about, and that's the interval from 9 to 16. So on our graph, that would be between year 9, which we just looked at a minute ago. Let's see, I'm going to go with purple. And year 16 is over here. So if we're comparing those 2 points to think about the average rate of change, it looks like it increased in the y direction, so it went up. Again, these are slopes, so we always want to do the rise over the run. It went up pretty close to 1,000, and it goes over between 9 and 16 would be 7. So if we calculate that, 1,000 divided by 7, I can't do this one in my head. I probably should be able to, but I can't. 142, or maybe if we round that to 143. So in the context of our music festival, that means between the ninth and the 16th year, the attendance was increasing on average by 143 people per year. So a little bit faster growth during that second time period. Okay, now we're going to switch over to, instead of finding an average rate of change from a picture of a function or a graph, we're going to look at what the average rate of change is for a function when we're looking at a table that represents that function. So for function h of x, we're interested in the average rate of change over the interval from -1 to 7. Now this is an interval. These are both x values. It's from the x value of -1 to the x value of 7. Typically when you're talking about average rate of change, we will use most of the time square brackets for that. We're sort of including those points in what we're thinking about. So if I look over at my table, I can see my x1 right here and my x2 right here. Those are the 2 points we're going to use. And remember, the average rate of change is all about finding the slope, slope if we averaged out that curve. So when we think about it, we can use the slope formula, which you are familiar with, y2 minus y1 over x2 minus x1. And I showed you, the function notation version of that, but they're really the same thing. It's the change in the y direction, or the rise, divided by the change in the x direction, which we sometimes refer to as the run. So for this function h of x, we're going to do 5 minus -1. So that's y2 minus y1. And we'll divide that by x2 minus x1, 7 minus -1. So that leaves us with a 6 over 8, which reduces to 3/4. So for this interval from -1 to 7, this function, whatever it is increasing on average over that interval with a magnitude of increase of about 3/4. So it's not growing super fast, but it is increasing on average over that interval. Okay, here's another one to try just for a bit of practice. Function k of x is represented in this table. I want to know the average rate of change over the interval from -4 to -2. Again, these are the x values. From -4, here it is on our table, up to -2. And there's that point on our table. So if we do our slope formula, y2 minus y1 over x2 minus x1. For this function, for this interval, it would be -2 minus 6 over -2 minus -4. Careful with your negatives. So we get -8 divided by 2, which simplifies to -4. So for this function k of x over this interval from -4 to -2, it is on average decreasing pretty quickly. -4 is a pretty rapid decrease. Okay, one more from a table. In 2008, approximately 66 million households had both a landline and a cell phone. That's on our table right here. And then our table also includes data from some other years. We're going to use this table to calculate the average rate of change for the interval from 2008 to 2011. So we'll be using this first point listed on our table and the last point. Again, we want to do the change in the y's over the change in the x's, or find that average slope. So for this situation, we would do the 51 minus the 66. Those are the y values, and we're going to divide it by the change in the x values. So we end up with -15 divided by 3, which gives us an average rate of change of -5. So how can we interpret this in terms of this problem? Well, it means that over that interval, on average, the function is decreasing, and it's decreasing by a magnitude on average of about 5 million per year. So people aren't as often having both a landline and a cell phone. Probably it means that they're just having a cell phone and not keeping their landline connected. Okay, another type of average rate of change. I mean, it's all the same average rate of change, but sometimes we don't have a graph or a table. Sometimes all we know about the function is the equation of that function. So here's function g of x. It's equal to x to the third power minus x. We want to know the average rate of change over the interval from 1 to 2. So those are our two x values. I think that the easiest way to do this is probably to build your own little table. Or I suppose if you had a particular affinity to graphing, you could maybe try graphing it. So we are interested in the two x values 1 and 2. And to fill in our table, we just need to plug in each of these x values into our function. So for the first one, if we plug 1 into our function, we get 1 to the third power minus 1. Well, that happens to be 0. And if we substitute in a value of 2 for x, we get 2 to the third minus 2, and that is 6. 2 to the third is 8, and if we subtract 2, we get 6. So essentially, we're just building our own table, and we'll do it exactly the same as we just did it in the problem prior. We'll just find the slope between those 2 points, and that gives us the average rate of change. So for this one, we would have 6 minus 0, and we'll divide that by 2 minus 1, and that's 6 over 1, which just is the same as 6. So for g of x, the average rate of change over the interval from -1 to 2 is 6. On average, it is increasing quite a bit. Okay, another one to try. Again, I think if you just have the function, probably the best way to keep track of what you're doing and think about it is to make your own table. Our interval here is from 4 to 9. So if we substitute each of those values into our function, we get a y value of 2 when we substitute in 4, and we get a value of 3 when we substitute in the 9. So to calculate our average rate of change, we do the change in the y values divided by the change in the x values. So we end up with 1/5. Again, for what that means for f of x is that for that particular interval from 4 to 9, the function is increasing. It's not increasing very quickly. It's an average rate of change of just 1/5, which is a pretty small rate of change, but it is increasing. Okay, we're almost to the end. So one of the things that we often think about with average rate of change is not just what the average rate of change of a particular function is, but we want to maybe compare some functions and decide which one has a greater average rate of change over the interval. So that's what we're going to do for the next two problems, is compare two functions. So over the interval from -1 to 8, I want to know which of these two functions has a greater average rate of change. Function f of x is given to me in a table. Function g of x is shown on the graph. So let's start with function g of x. Again, we started with graphs at the beginning. To find that average rate of change, I just want to count out what the slope is between this point -1, -2, and the other end of my interval is where x is equal to 8, so here. So if I look at the behavior of the function, it looks like it's increasing pretty quickly through here. Lots of fast increasing, and then it kind of levels out and it isn't increasing quite as fast. Well, I want to average that out. It's going to be this straight line. And so if I think about what's happening, this thing is going up 1, 2, 3, 4, 5, 6, and over 6, 7, 8, 9 over 9. So that reduces to 2/3. So my average rate of change for g of x is 2/3. Well, now let's look at f of x. F of x is given to us in the table. Again, we're interested in the interval from -1 to 8. So if we calculate that average rate of change, we do y2 minus y1. Wow, good parenthesis usage. And we subtract the x's for the denominator x, 2 minus x1. Okay, well that simplifies to 3 over 9, which reduces to 1/3. So our average rate of change for function f of x for the interval from -1 to 8 is 1/3. So our job was to compare the two and decide which of those two functions had a greater average rate of change. And it looks to me like 2/3 is greater than 1/3. So function, that one is g of x, has a greater average rate of change. Now again, the interval is really important here. Over the interval from -1 to 8. So if we had looked at a different interval, potentially f of x could have had a greater average rate of change. The decision of which one has a greater average rate of change is very specific to that interval. For the interval we were interested in, g of x had a greater average rate of change. Okay, one last one to practice. We're looking at the interval from -3 to 0. I want to know which of the functions has a greater average rate of change. So for function h of x, for the interval from -3 to 0, the average rate of change would be 7 minus 1 over 0 minus -3. That's 6 over 3, which reduces to 2. For function f of x, I'm going to make my own little table to keep track of all my data. We're interested in the interval from -3 to 0. Again, you could make a table that had more values in it, but there's no need to. The only two that we are interested in right now, the only two x values are -3 and 0. So if we put -3 into our function for x, be really careful here. You've got to put that -3 in parentheses and then square it. Plus 6 times -3 plus 12. If we calculate that, you should end up with a value of 3. If you didn't end up with a value of 3, it is most likely because you forgot to use parentheses here to show that the quantity that we're squaring is -3. For the second row of our table, we're going to substitute in the value 0. And we end up with a y value of 12. So to calculate the average rate of change, we take 12 and subtract 3, y2 minus y1, and we do the difference of the x's in the denominator. So that's 9 divided by 3, which simplifies to 3. So it looks like out of these two functions, h of x and f of x, over the interval from -3 to 0, function f of x has a greater average rate of change. Okay, so that is essentially it. We just sort of talked about this concept of average rate of change. Remember, average rate of change is essentially finding the slope of the secant line, or if you averaged out that curve over whatever interval you have given to you, it's giving you the slope there. So your assignment is green in your notes, and I would like to remind you that next time on, let's see, Thursday, we will be doing a test review, and your test will be given to you on Monday. So if you need some help with any of these concepts, make sure you come in and get some help before Monday when your test will be given. All right, thank you.